Hello. In the continuation with our last lecture, where we had started with cation analysis in case of a mixture, where the detection of a mixture first needs to be started with the preparation of the original solution or OS. So, if the mixture is insoluble in dilute HCl, then it is dissolved in concentrated HCl by adding concentrated HCl and boiling it. And as discussed in the previous lecture, that if still the mixture is insoluble, then it is analyzed separately under the scheme of insolubles. This solution above is then diluted with distilled water and centrifuged. Upon centrifugation, a residue is obtained which indicates that group 1 cations are present in the mixture. In the centrifugate, we test for group 2 cation onwards till group 6, and then in the residue, as we start with the analysis of group 1 cations, wherein the residue is taken and water is added to it. Whatever cations which are present in group 1 are all generally soluble in water. The solution is then boiled and then centrifuged. A residue is obtained which contains silver ions and mercurous ions as silver chloride and mercury chloride. In the centrifugate, we test for lead as lead chloride. We divide the centrifugate first. We test for lead ions in the mixture, wherein the centrifugate is first divided into 3 parts. To the first part, the centrifugate is cooled, and then we observed, upon cooling, we observe shining white crystals of lead chloride, because lead chloride is soluble in hot solution and it precipitates out in the cold. To the second part of the centrifugate, we add potassium chromate solution. Upon adding potassium chromate, yellow precipitates, as we can see on the right hand side, the second picture, yellow precipitates of lead chromate are obtained. To the third part of the centrifugate, we add concentrated sulfuric acid, and if lead is present, then again white precipitates of lead sulfate are obtained. Is the chemistry involved in the particular tests? The first one, wherein lead chloride is reacted with potassium chromate to produce lead chromate, and lead chromate is the one which is giving the yellow precipitates. Then again lead chloride is reacting with sulfuric acid to produce lead sulfate, which is again giving white precipitates, which is the third test as mentioned in the previous slide. Lead chloride is soluble in hot solution and it precipitates out in the cold. Therefore, as in the part 1, upon cooling, shining crystals of lead chloride are obtained. And why lead chloride? Because HCl has been used as the original solution. Coming to the residue part, which might contain silver ions and mercurous ions, the residue is taken and ammonia solution is added to it. Ammonia, or we can also say ammonium hydroxide, is added to it, and this is then shaken well. Again, upon adding ammonia, if a residue is obtained, then the semi-micro test tube is centrifuged. This residue is dissolved in aqua regia and centrifuged. Since this residue will not dissolve in any other acid, therefore it needs to be dissolved in aqua regia. And we all know what is aqua regia, which is a mixture of HCl and nitric acid in a 3:1 ratio. To this solution, stannous chloride solution is added. Upon adding stannous chloride, if we obtain white precipitates which are gradually turning grey, then it confirms the presence of mercurous ions in the mixture. And as the equation goes, mercurous chloride is reacting with HCl and O, that is nascent oxygen, which is obtained from nitric acid, that is the combination of HCl and nitric acid, which is aqua regia, produces HgCl2, and this HgCl2 reacts with SnCl2, which is stannous chloride, to produce mercury, which is grey or blackish in color along with stannic chloride. Coming to the centrifugate part, which was obtained after adding ammonia, wherein ammonia was added to the residue and a precipitate was obtained. In the precipitate we had tested for mercurous ions. In the centrifugate or in the supernatant or the solution, after separating the residue, we test for silver ions. Now, these silver ions have formed a silver amine complex in ammonia and they have passed into the soluble state. So, this centrifugate or the solution is taken and is divided into two parts to confirm the presence of silver ions. To the first part, dilute nitric acid is added. Upon addition of dilute nitric acid, if curdy white precipitates are obtained, then it confirms the presence of silver ions in the mixture. These curdy white precipitates are due to the formation of silver chloride, as can be seen by the equation which is written below. That is, a silver amine complex on reaction with dilute nitric acid results in the precipitation of silver chloride as a white precipitate, wherein the silver amine complex breaks upon the addition of nitric acid. To the second part, potassium chromate is added. Upon addition of potassium chromate, if brick red precipitates are observed, it confirms the presence of silver ions in the mixture. These brick red precipitates are of silver chromate, which are evident from the equation given below, wherein the silver amine complex reacts with potassium chromate to form Ag2CrO4, which is silver chromate, giving a brick red precipitates. These two tests confirm the presence of silver ions in the mixture. So, upon this we have completed the analysis of group 1, wherein we have detected the presence of lead, mercurous and silver ions. After that, we move on to the analysis of group 2 cations. Now, the centrifugate which is obtained after separating group 1 cations in the form of the residue is termed as group 1 centrifugate, in which the presence of group 2 cations is analyzed. That is, the solution which was obtained after separating group 1 as a residue, in which we had detected the presence of lead, mercurous and silver. Now, the solution which is obtained is used for the detection of group 2 cations. So, group 1 centrifugate is now heated and H2S gas is passed through it with constant stirring. At this point, before passing H2S, a little bit more of hydrochloric acid HCl can be added to it, although HCl is already present because the OS has been prepared in HCl. If the residue is obtained on passing H2S through the centrifugate, then this residue is analyzed for the presence of group 2 cations, which include cuprous, cadmium, bismuth and lead. Mercurous, again, which is sometimes missed out in group 1, arsenic, antimony and bismuth ions. So, these are the cations which are detected as a part of group 2 cation analysis. The H2S gas is passed after the dilution of group 1 centrifugate also to check for the complete precipitation of cadmium ions. Since cadmium ions have a higher solubility product and its yellow precipitate, that is yellow precipitate of cadmium sulfide upon passing H2S, come out only on dilution. So, these are the equations or the chemistry involved and the various color of the precipitates, as we can see in the adjoining figure. Lead ions on reacting with H2S produce lead sulfide, which give a black color precipitate or a residue. Mercuric ions on reaction with H2S produce mercuric sulfide, which again produce a black color residue. Cupric ions on reaction with H2S produce cupric sulfide, which again have a black color residue. That means all these three ions, that is lead, mercury and copper, these produce a black color residue on passing H2S. Bismuth ions on reaction with H2S produce bismuth sulfide which have brown color. Cadmium on passing H2S produce cadmium sulfide which produces a yellow color residue, as you can see in the joining figure. Arsenic ions on reaction with H2S produce arsenic sulfide, again a yellow color residue. Antimony with H2S produces antimonide sulfide which is giving an orange color residue, and stannous ions on reaction with H2S produce stannous sulfide which give a black color residue again. So certain cations give a similar color of the residue and some have a specific color of the residue. So for example, if on passing H2S we obtain a black color residue, then that may be due to any of the cations mentioned over here, since black color can mask even yellow and orange colors. Whereas upon passing H2S, if specifically yellow color residue is obtained, then we can assume safely that lead, mercury, copper, bismuth and stannous are absent in the mixture, and that yellow may be due to cadmium or arsenic. So specifically cadmium and arsenic need to be detected in that group. If on passing H2S only orange color precipitates are observed, then it can be assumed that this mixture contains only antimony in the group 2 cation series. The solution obtained after passing H2S is then centrifuged and the residue is analyzed for group 2, whereas the centrifugate is kept for testing the cations of group 3 onwards, and this centrifugate is called the group 2 centrifugate. So in the residue we will be now testing for the cations which have been just mentioned: lead, mercury, copper, bismuth, cadmium, arsenic, antimony and tin. The residue is then collected and washed with water. Then yellow ammonium sulfide solution is added. Yellow ammonium sulfide is also called ammonium polysulfide, which is prepared by passing excess of H2S through ammonium sulfide solution. It produces a polysulfide solution. Excess of sulfur is being produced. After that, a few drops of NaOH solution are added, sodium hydroxide, and the semi-micro test tube is warmed and centrifuged. If upon adding NaOH we obtain a residue, then that residue is analyzed for group 2A cation, since group 2 is further divided into group 2A and group 2B. So in the residue we analyze group 2A cations, in the centrifugate we analyze group 2B cations. If upon adding NaOH no residue is obtained, we can assume that cations belonging to group 2A are absent, and we just analyze the centrifugate for the presence of group 2B cations. Now what are the cations belonging to group 2A and group 2B and how they have been separated is what we need to know. So group 2A contains cations like lead, mercury, bismuth, copper and cadmium, and the remaining cations belonging to group 2B. So if a residue is obtained, this is washed with first hot water, then dilute nitric acid is added to it, and the solution is boiled for few minutes. Then it is centrifuged. Upon centrifugation, if a residue is obtained, then that residue will be black in color, and it will be due to mercurous sulfide. Since any residue pertaining to mercury is not soluble in any of the acids, it is only soluble in aqua regia. So again this residue also needs to be dissolved in aqua regia and then centrifuged. After that, stannous chloride solution is added. After the addition of stannous chloride, if white precipitates turning grey are observed, it confirms the presence of mercuric ions in the mixture. Mercurous ions can come both in group 1 as well as in group 2. So, if in group 1 mercurous ions have not been separated or not been eliminated totally, then they can also come out in group 2 cation analysis. So, as the chemistry goes, mercurous sulfide reacts with aqua regia, that is a combination of HCl and nascent oxygen to produce mercury chloride, which reacts with stannous chloride to produce again mercury, which is giving a elemental mercury, which is giving a black color residue along with stannic chloride. Now, a small portion of the centrifugate is treated with a few drops of dilute sulfuric acid and alcohol. The small portion needs to be first tested with the dilute sulfuric acid and alcohol, because if at all we observe the white precipitate, then to the remaining solution we need to add sulfuric acid, because unnecessarily addition of acids and other reagents need to be avoided to facilitate the further analysis of the cations. So, upon the addition of dilute sulfuric acid and alcohol to a small portion, if a white precipitate is observed, this indicates the presence of lead in the mixture as lead sulfate, and this will come only if lead has not been completely removed from group 1. Then in that case, sulfuric acid and alcohol is added to the remaining centrifugate also to separate out lead as lead sulfate. And in this case, if to a small portion when dilute sulfuric acid and alcohol is added, no precipitates are observed, then to the remaining solution dilute sulfuric acid and alcohol need not be added, which indicates the absence of lead in the mixture. So, in case no white precipitate is obtained, the solution is used for the test of remaining ions apart from lead, because this has indicated that lead is absent. So, if upon the addition of sulfuric acid, lead sulfide precipitates out as lead sulfate, which gives a white precipitate in the presence of alcohol. Alcohol is just facilitating the appearance of precipitates. Now, we assume that the mixture contains lead and the residue has been obtained, which is of lead sulfate. So, this residue is tested again for the confirmation of lead ions by adding ammonium acetate to the residue. Upon adding ammonium acetate, lead sulfates dissolves in it to form lead acetate. After that, to this solution potassium chromate is added, because any test which needs to be performed is to be performed in a solution only when the residue moves on to the solution form. So, this residue also needs to be dissolved first in ammonium acetate. After that, potassium chromate is added. Upon adding potassium chromate, if a yellow residue is obtained, it confirms the presence of lead ions due to the formation of lead chromate. And the equation which has already been discussed, lead chromate forms upon the addition of potassium chromate. The centrifugate is now tested for the presence of copper ions, bismuth ions and cadmium ions, because we have already tested for lead ions over here and mercurous ions over here. So, now the remaining ions which are in group 2A are bismuth, copper and cadmium, which will now be detected. So, to the centrifugate, ammonia solution is added in excess dropwise and then it is centrifuged. Upon adding ammonia solution, if a residue is obtained, then that residue will be white in color and it will be due to the presence of bismuth ions in the mixture, because bismuth ions will precipitate out as bismuth hydroxide. And in the centrifugate, we will test for copper ions and cadmium ions, because copper and cadmium both will form their respective amine complexes in the excess of ammonia solution. They do not precipitate out as their hydroxides, because excess of ammonia has been added, only bismuth precipitates out. So, this is the chemistry involved, where we can see that bismuth reacts with ammonia or ammonium hydroxide to give bismuth hydroxide, which is a white PPT. Copper ions react with ammonia to give cupramine complex, which is a blue colored solution, as you can see in the adjoining figure. Cadmium ions react with ammonia to produce a cadmium amine solution, which is a colorless solution. So, both copper and cadmium go into the solution upon reaction with ammonia, whereas bismuth precipitates out upon reaction with ammonia. So, this is how bismuth, copper and cadmium are separated from each other. Coming to the residue part, wherein we confirm the presence of bismuth ions now, because any residue which is obtained, or for that matter any centrifugate which is there, has to be analyzed further for the confirmation of the cations. So, the white residues of bismuth hydroxide is dissolved in concentrated HCl and is dissolved into 3 parts. Again dissolved because whatever tests needs to be performed are performed only in solutions. Residue cannot give any kind of tests. So, after dividing the solution into 3 parts, the first part is taken and is diluted with water. Upon adding water, if there is a white turbidity observed in the solution, as you can see in the joining figure, then that white turbidity is due to the formation of bismuth oxychloride. And the reaction which explains it, bismuth hydroxide upon reaction with HCl dissolves in it to produce bismuth chloride. This bismuth chloride upon reaction with water or upon dilution produces bismuth oxychloride, which is a white turbidity or a white color precipitate which is spread out in the solution. To the second part of the centrifugate, sodium cyanide solution is added. Sodium cyanide has the formula Na2SNO2, which is actually prepared by the reaction of stannous chloride with sodium hydroxide. Because sodium cyanide solution actually is not available as such, it needs to be prepared first by the reaction of sodium hydroxide and stannous chloride. So, upon adding sodium cyanide solution, if a white precipitate turning black is observed, that confirms the presence of bismuth ions in the mixture. And the reaction which explains this test, wherein the bismuth chloride ions react with sodium cyanide solution, bismuth chloride solution reacts with sodium cyanide solution to form bismuth, which precipitates out as a black precipitate, and sodium cyanide is further oxidized. In the centrifugate, we confirm the presence of copper ions and cadmium ions. Now, if the centrifugate is colorless, then copper ions are absent. If the centrifugate is blue, then copper ions are present in the solution. The centrifugate is then acidified with dilute acetic acid, and to this potassium ferricyanide is added. Upon the addition of potassium ferrocyanide, if chocolate brown precipitates are observed, this confirms the presence of cuprous ions in the mixture. If white precipitates are observed, this confirms the presence of cadmium ions in the mixture. So, if the centrifugate is colorless, we can safely assume that the mixture does not contain copper. If the centrifugate is blue, then we can safely assume that the mixture does contain copper. Cadmium may or may not be present, because cadmium centrifugate is colorless, whereas copper centrifugate, copper solution is blue in color. The chemistry which is explaining the above test, cupramine complex reacts with acetic acid to produce copper ions and ammonium acetate solution, which is explaining that how copper ions are formed. These copper ions react with potassium ferrocyanide solution to produce cupric ferrocyanide, which is providing a chocolate brown precipitate, and the color can be seen in the adjoining figure. Cadmium ions upon reaction with potassium ferrocyanide produce cadmium ferrocyanide, which is giving a white color precipitate. Now, if both cadmium and copper are present in the mixture, then cadmium needs to be detected in the presence of copper, because the test we have just discussed is with potassium ferrocyanide is giving color of a chocolate brown and white precipitate in both the cases. So, how to distinguish between these two cations is now what we need to know. So, for testing cadmium in presence of copper, the centrifugate is acidified with dilute HCl and iron wire is added to it. It is then heated and then centrifuged. To this, H2S is passed. If a yellow precipitate is obtained now, it confirms the presence of cadmium ions in the mixture. Now, how does this happen and what is the use of iron wire which we have added to distinguish between cadmium and copper? Iron wire reduces copper 2 to copper 1. That means it reduces cupric ions to cuprous ions and hence it masks the cuprous ions because cuprous ions do not precipitate as its sulfide on passing H2S. So, on passing H2S only Cu2 will get precipitated as copper sulfide and not Cu1. So, iron wire converts copper 2 to copper 1 and hence now the precipitates which we obtain are of only cadmium and not of copper. And this finishes with our analysis of group 2A. Thank you so much.